I have a question. Is it important to know, what causes the loss of a leading group? Do you need to know that? Okay.
How are we at chapter 7?
Chapter 6 is just a review.
Yeah, you're not going to be asked like questions on chapter 6. It's like laying the grounds. So then for SN2, first we start with a nucleophilic attack. So in SN1, it was the leaving group leaving first, but in SN2, the nucleophile is going to attack first, and then the leaving group is going to leave. And same thing, nucleophile replaces the leaving group. So you would result in the same thing, but it's just different.
So it's
steps.
two-step process.
Exactly.
What's
One
it?
step versus two step. That's what it says.
What's a nucleophile?
A nucleophile or a base is something that like readily donates electrons to form a bond. For E2, and also for E2, notice, or for elimination reactions in general, they're going to form alkenes of high bonds. And the substitution, as the name suggests, will substitute the leaving group with the nucleophile. For E2, the base will attack a beta hydrogen, which will then result in the leaving group to leave, and then a pi bond forms, resulting in an alkene.
Can you show the intermediate steps? Like what happens when the nucleotide attacks, and then what happens to the charge? Is it does it become a carbocation? Like when the nucleo thing attacks, and the carbon.
This one?
Yeah. So when it attacks, what happens to the charge is what I mean. The carbon.
When it attacks, the leaving group kind of just gets removed.
Yeah. Or it happens simultaneously.
Yeah.
Okay.
And then it'll be replaced by whatever nucleophile attacked it. Yeah, but you don't really need to know you don't need to really draw all of this out. Like on the exam, if you just put this, that's fine.
Okay.
Because you know that it'll just be substituted.
Oh.
Yeah.
And anything that's like second order will always be one step. Like automatically one and then the other.
Second.
Like SM2 and E2.
So the difference we were saying was that SM1 and E1 is like one step versus here is two steps. See how first the base attacks and then the leaving group leaves versus here the leaving group leaves and then
I thought it was the opposite. Because I think we drew the diagram for SM2, it was always one pump, and then for SM1 today, we showed us it could be like 2 or 3 pumps.
What do you mean by two? The arrows?
It's like one step.
Oh.
On the diagram. But I think I only saw one step for SM2 and E2.
I'll check on that. I don't think it's necessary to. But this is important, the rearrangement. So for SN1 and E1, always check for rearrangement, and you want to increase the stability. So primary is going to be, or secondary is going to be more stable than primary, which is going to, tertiary is going to be more stable than both of them. There's two ways you can rearrange. One's the hydride shift, where in this one you see that this carbocation is secondary, but it has a possibility of becoming tertiary, right? So this carbon has a hydrogen, and that hydrogen can then shift where this positive charge is. So it goes here, but you don't really have to draw hydrogens. And then the carbocation will move there and become tertiary. Here, same thing, except this carbon doesn't have a hydrogen, but it does have 3 methyls, right? So you can have a methyl shift where one of the methyls moves there instead, and then it forms this. And you do have to draw the methyl moving.
What does primary, secondary, and tertiary mean?
Oh yeah, okay. So the carbocation is on this carbon, right? And this carbon is attached to two other carbons.
Okay.
So that's secondary.
Is it only replaced with, does it only count carbons?
Yeah. Or yeah. So like this over here is attached to three
Three
carbons.
carbons.
So it's tertiary.
Tertiary.
Yeah.
What about the one in the middle
This one?
of, the one above it where it's attached to 4 carbons?
So the positive
No,
charge is on
not the
this.
positive one, the one next to it. It's
The
attached,
one with
the one in the
4
center,
metals.
yep, right there. What is that?
This one we aren't writing primary, secondary, tertiary because we only do that for where the carbocation is.
So where there's a plus charge.
Yeah,
Oh,
because that's what you're focused on, stabilizing. And then this is a table that kind of helps determine which reaction to do. So if you have a primary substrate, right, this Br is only attached to one carbon, then you're going to determine which reaction to do based on the reagents that you're given. So if it's a protic solvent like water, you look at these like SN2. Aprotic like Br minus or Cn minus, SN2. Small bases, generally it'll be OH minus or CH3O minus. And bulky CH33CO minus is the most common one that I've seen.
I think that's the only one it's gonna
The
be.
only one, yeah, on this exam.
Substrate, okay.
So for the secondary BR, I think that's the primary, never mind.
Primary.
Yeah, this one. So BR would leave, right? And then if we put it in a protic solvent, it would have an OH instead? Is that okay?
Yeah.
And then if it's in a protic solvent, it gets an OH, there will be an H plus, right? Where does that matter? Like where that goes?
No, you don't even have to write that,
Okay.
like any other products for me.
Why is it a secondary BR?
That one,
Yeah.
because it's attached to two carbons. So in this case, we're looking at the substrate, right, and not the carbon that it's, so the positive charge, we look at the carbon that it's on, right?
Okay.
And how many carbon that carbon is attached to. For substrates, look at
The
how many
substrate
carbon are attached to the substrate itself. So this Br has one carbon, this Br has two.
So we're looking at the carbon that's attached to the BR.
No, that's for when you have a positive charge, you look at the carbon that it's on.
Okay.
And for, yeah.
Yeah, that's it, yeah.
You guys go over Zaitsev-Hoffman? Okay.
I wasn't here.
Zaitsev is the more substituted alkene, and Hoffman is less substituted. So for example, say, Zaitsev in this case would be, so like Zaitsev would be secondary, Hoffman primary, right?
Yeah, I don't get that.
Oh yeah, this one is a bit different too because you're looking at the carbon that the alkene is attached to. So this alkene is connected to two carbons, and this one only one. Or
That one's
no,
also
this is a
two.
bad example.
So Hoffman is one?
Yeah, or not always one. Sorry, I need to find a better example.
Is it basically like how many carbons the alkene is connected to?
Yeah, so
And
the
like-
Zaitsev will have more connected to it.
And it's always like we're gonna be given two and then we're gonna be comparing both of them, or? Because
We'll see in the problems, you'll have like options of where to draw the alkene, and depending on which I'll get to right now. So E1 will always be side sub. So you're always going to choose to put the alkene where it's going to be connected to more carbons. And then for E2, it'll be depending. So if it's a small base, it'll be side sub.
Yeah, he did speak about this.
Okay.
I don't remember the side sub with Hoffman, but it's just E1 will always be more substituents.
Yeah.
E2 depends on the bases of, and then that determines the amount of substituents. If it's a bulky, it's
If it's bulky, it'll be Hoffman.
When is this bulky? What is it's almost
It's-
like
So it'll be this. If
Yeah.
you see this, then that's bulky. Because in fact, if you see this, you don't even have to like see if it's primary or secondary. It'll always be E2 Hoffman.
Would it be drawn out or would we be given this? Like CH3 CO minus.
All the ones I've seen were written like this.
Okay.
what does E2 mean?
Elimination two.
Elimination to reaction right there. Yeah. And then an exception for this one. So usually if it's E2 small base, it'll be side sub. But for stereospecificity, so for example, you might be given
Let me use this whole weekend to learn.
like this BR, right, is
This
on
whole
the
weekend to
wedge.
learn about this.
And normally for side sub, you would want to put it here, right? But, or rather,
There's no alkene here. I thought, so can Zaitsev and Hoffman be in anywhere? Because I don't see an alkene here.
no, this is for when we're trying to add an alkene.
Oh,
Yeah.
okay, oh, right.
So, when we try to get rid of the BR and then add an alkene, either here or here, let's say. Normally for Zaitsev, you would want it here since it'll be substituted more. But for stereospecificity, if you see that the BR is on a wedge, that means the beta hydrogen that you choose has to be on a dash. So since this hydrogen is also on a wedge, you can't put the alkene there. And we'll do a problem like that, but that's like one of the trickier exceptions.
So if the hydrogen is facing the front, you cannot.
So they have to be opposite. So if BR is on a wedge, the hydrogen, the beta hydrogen that you
Has to be
choose
the
has to
back.
be dashed and vice versa.
So, one point in the class, he used, he used like the hexane, and then he said it has to be anti. But then when he used like a butane, he said they have to be on the same plane and opposite. I don't understand why for that one they have to be on the same plane, but for hexane they have to be opposite.
Do you have the problem? Also, did you guys get this yet?
We haven't practice, but now. But he hasn't explained it yet.
This is from chapter 8, but all of the problems for chapter 7 are also mixed in with these reactions. But this is nice because like it lists all of them
Are
out.
we getting that on the
Yeah, it's on the exam.
Oh,
Yeah.
Question, do you put the slides for chapter 5?
Yeah, it's on the Excel spreadsheet.
For a hydrogen shift, you know how you can remove the carbon charge? Do you have to put arrows?
You don't have to. Yeah, because on the exam it'll just ask you to draw out the product. So as long as you have that. Yeah, but if you want to like keep track. I'm gonna erase this. I'm gonna take a picture.
Yeah. What exactly does this?
What was that?
What exactly does it mean? Like,